Hello, my name is Hagmar and I am a junior majoring in material science and engineering. This fall, I collaborated with the FAIRY research group from the Chemical Engineering and Material Science Department to develop a formulation of cadmium selenide nanoplatelet ink for micropatterning. To better understand the purpose of the project, it's important to introduce the concept of metamaterials. Metamaterials are composite engineered materials with properties that depend not only on their chemical composition, but also on the array geometry. That is, how its components are organized in the structure. Metamaterials can be used in many optoelectronic applications, such as in encryption, photovoltaics, and optical displays. Due to their complex geometry, metamaterial fabrication is very challenging, and one of the goals of this project is to implement a fabrication method to create light-emitting metamaterials using semiconductor nanoplatelets, which are a type of nanocrystal with light emission confined to 2 dimensions. Cadmium selenide nanoplatelets were synthesized using air-free chemistry techniques in a shrink line and glove box. The synthesis consisted of multiple heating and cooling cycles of an initial base solution of 1-octadecene in cadmium myristate, adding selenium powder, cadmium acetate, and, at the last cooling step, oleic acid ligands. The nanoplatelets were suspended in hexanes in various concentrations. As you can see in the figure at the center, the nanoplatelets exhibit photoluminescence under UV light. They were characterized using UV-vis spectroscopy, and we can see in the figure at the top right its spectrum compared to other photoluminescent nanocrystals commonly synthesized in the FAIRY group. In the bottom right, we can also see a transmission electron microscopy image taken of the nanoplatelets in a randomly assembled fashion. Part of the project focused on the implementation of a roll-to-roll compatible metamaterial fabrication technique. This is an additive manufacturing technique that can be easily scaled up and can be applied to flexible substrates. We made PDMS stamps using a silicon mold that was patterned with photolithography. The stamps were treated with Cytop and used to create NOAA micropatterns onto glass substrates. These micropatterns consisted of wells with feature sizes of 3 microns and 1.5 microns. Compatible process, we use the nanoplatelet suspensions as inks and drag them across a substrate using an automated stage, as we can see in the schematic on the right. We varied both the concentration of the ink and the dragging speed. The samples were characterized using optical microscopy under a 405 nanometer pulse laser. The features we looked for were selective dewetting, that is, the ink will stay exclusively inside of the wells, and continuity in the pattern. With a 12 mg per milliliter ink, we could see that for the speeds of 0.4 and 0.7 millimeters per second, we were able to observe an incomplete dewetting for the 3 micron feature size. However, no dewetting was observed for the 1.5 micron samples. At higher speeds of 0.85 and 1 millimeter per second, the results were better for the 1.5 micron size. However, we can see that the very center of the well is not completely filled, which we call a coffee ring effect. Working with the 10 mg per milliliter suspension, the results are overall better. The 0.7 millimeter per second speed now shows better selective dewetting for the 1.5 micron samples, whereas we can see the coffee ring effect in the 3 micron samples, and in both feature sizes for the speed of 0.85 millimeters per second. We can also see the lack of uniformity in the 1.5 micron feature size, which is very evident from this large splotch of ink floating on top of the wells. 5 mg per milliliter concentration, the 0.7 millimeter per second dragging speed has many similar effects to the one presented in the previous slide. However, the 0.85 millimeter per second speed seemed to perform much better for the 3 micron size, showing a much more complete dewetting without a coffee ring effect. The 1.5 micron feature size, though, lacks uniformity and has poor dewetting. To summarize what has been done in this project, we've synthesized cadmium selenide nanoplatelets and suspended them in hexanes to create inks for metamaterial fabrication. We made microwells via a stamping mechanism based on photolithography and performed a surface treatment on the patterns. We reached the conclusion that the concentrations of 10 mg per milliliter and 5 mg per milliliter worked best for this experiment, and that lower dragging speeds of 0.7 millimeter per second are more effective for the 1.5 micron feature sizes, and faster speeds of 0.85 millimeter per second are more appropriate for the 3 micron feature sizes. As for future work, we plan on taking photoluminescence spectroscopy measurements of the pattern samples, improving surface treatment techniques, as well as refining the ink dragging method. and we plan to experiment with different organic solvents such as octane to suspend the nanoplatelets. Here are some of the references that we used for this project. I'd like to thank the Ferry Group for the opportunity to work with them on this project, as well as the Francis Group for allowing me to use some of their facilities and equipment. I'd also like to acknowledge the Undergraduate Research Opportunities Program for sponsoring this project. Thank you so much for listening to my presentation.